Okay, so here we are. New section for today. We're going to start with section 2.4. There's several things in 2.4 that I'm going to not spend class time on. You are responsible for it, but again, tough choices. I think most of it's kind of pretty readable. But there is one point in particular that I think really needs to be commented on, and that is about the linearity of differentiation. Now, let me be clear here. I am not talking about the linearity of the derivative matrix, right? The derivative matrix, of course that's linear. It's a matrix. All matrices as functions are linear, right? It's one of the first things you learn in a linear algebra class. I'm talking about something different. I'm talking about the process of differentiation, the process by which we take a differentiable function like f and turn it into a derivative matrix. Right? So that's not the same as the derivative matrix itself. We're not talking about this thing. Of course, that's linear. It's a matrix. We're talking about this thing, this act of differentiation. Right? So how do I know, in particular, that if I look at these inputs, keep in mind the inputs to the act of differentiation, those inputs are functions, not vectors. They're functions. And if I were to take a linear combination of functions, do I get, when I take the derivative matrix, the corresponding linear combination of their individual derivative matrices, right? And this is a very different and kind of more sophisticated question. Okay, so turns out, yeah, it is. Differentiation is linear. And here is an example of this in action, the fact that differentiation is linear. Now this is just a plug and chug kind of a thing. I'm going to go, whoops, sorry. Working with my left hand today, everything's going to be a little clunky and slow. Sorry about that. So here you'll notice I have a couple of differentiable functions and their derivatives. Right? Two variables in, two variables out. Easy to compute these derivative matrices. Of course, obviously, make sure you can do that. Make sure you know how to arrange these matrices. It's really easy, recall, to accidentally transpose derivative matrices. Keep in mind, columns correspond to input variables. Rows correspond to output variables. Okay, so there's a couple of functions, and then here is their, I made up a linear combination of them arbitrarily, 5 times f plus 6 times g. No particular reason, just an arbitrary linear combination. And you can work out what that function is. You can take its derivative matrix. Again, make sure you can do that. Okay, so the question is, does linearity work in this case? And it is just kind of a matter of writing down both sides of the question. I want to know if I look at a linear combination of the derivative matrices, is that the same as the derivative matrix of the linear combination? Well, this linear combination of the derivative matrices, I can just straight up compute. I can just plug in the derivative matrices df and dg. I can multiply all that out. And then, of course, I can take the derivative of the combination. The derivative of h is that. And you can directly confirm with arithmetic. This is just arithmetic. You can confirm that this arithmetic works. And as a result, we see that this expected linearity worked. Okay. Everybody on board? All right. So there is a single variable version of this, by the way. In single variable calculus, you may recall, and they say it differently, but they'll say, you can do differentiation term by term. What they mean there is if you take a derivative of a sum of two functions, you get the sum of the individual derivatives. of the individual functions, right? And it's something that we just kind of take for granted. It's like, yeah, you just go term by term. It's we're so accustomed to it we don't even notice it, right? And that's actually kind of a single variable analog of what we're observing here. Okay. Likewise with scalars and stuff like that. Okay. All right. Again, quick, wave of the hand. I'm going to suggest you all look through all of this on your own. Time being a critical factor, tough choices and all that. There is a product rule of sorts, and in some cases, and a quotient rule in some cases that you can write down. So again, it's just formulas. It's in the book. Take a look. Make sure you're comfortable with those formulas, etc. Okay. All right. Now, let's talk about higher order partials. You remember in single variable calculus, you could talk about higher derivatives, a second derivative, for example. And a second derivative is something you can algebraically do. It's something for which we have a geometric interpretation. It's about concavity, right? Second derivatives are concavity. On the graph, that's, again, calculus of graphs. That's specific only to graphs. Can you do anything like that for multivariable functions? And the answer is yes, but assuming nothing weird happens. But just notice real quick, if you have a function of a bunch of variables, if you take the partial also a function of all of those same variables. And so you can take a partial of it too. It's a pretty innocent observation. You can see that in action in the diagram I have down here. Here is a function of x and y. And notice when I take the x partial, or if I take the y partial, whatever, notice the results are also functions of x and y. And being as they are also functions of x and y, I can talk about, for example, the x partial's x partial, or the x partial's y partial, etc. That makes sense? Everybody happy with that? Okay, so a couple of little notational points to discuss here. I'm going to zoom in so we can see a little bit better. Here we go. When you have an x partial, and then if you were to take a y partial of that, how would we write that? Y partial of the x partial. So here's one notation that you could use. You could say, well, I literally write that I first took the x partial of the function f, and then after I took that x partial, I am pretty literally just going to take the y partial of that. And once you write down this here, you can see how that would motivate this notation there. Okay, so this is one of your alternative notations for a second derivative, specifically the y partial of the x partial. Okay, now on the other hand, here's a totally acceptable alternative notation. We use the sort of the Newton-like notation. And again, we're going to do the x partial first. Here I'm going to denote the x partial with a subscript. And then I'm going to take the y partial of that x partial. And of course, I'm going to represent that y partial with a subscript. And I think it's pretty plausible that we could abbreviate that like so. All right, so two different notations. Take your pick. Not important. Sometimes one of them makes more sense than the other. Either one of them's fine. Okay, now I do want to call your attention to one ugly little reality, and that is the way that these different notations kind of go down when you write the partial operators in the Leibniz notation. They're kind of on the left, if you will. And so successive partials that you might take, they sort of stack up toward the left. Whereas with the Newton ripoff notation here, we make them subscript on the right. And so they kind of, as you go along, they stack up to the right. So notice you can see that in these two alternative notations. Now these represent the same thing. Both of these, x partial first, y partial second, but notice the x and the y are in one order with one of them, but they're in the opposite order with the other one of them. And this is just unavoidable. This is, I can't get away from it. It's an unavoidable consequence, I would say, of how we write derivatives in the first place. So my advice on this, just be careful, right? Think it through. When you look at something like this, make sure to think carefully about, wait a minute, this is a shorthand for what, right? And then which one of these actually acts first, and et cetera. Okay. Everybody happy with that? Okay. All right. Cool. Let's see here. Now you'll notice in how all this worked out. In this case, the two what we call mixed partials, the y partial of the x partial, the x partial of the y partial, happen to be the same. Weird. Seems like a coincidence at first glance. Now, once you notice this, and by the way, very often when mathematicians see coincidences, they think, okay, there are no coincidences. There's a reason for this, right? Maybe there's an underlying reality here that we should be looking for, right? And you can persuade yourself without too much trouble that for polynomials, this is always going to work. Because in some sense, when you're taking derivatives, partial derivatives of polynomials, when you're taking the x partial, really only the x factor is involved with that. It doesn't do anything to the y factor. And then when you take the y partial, only the y factor is involved. The x partial isn't really doing anything. And so it's pretty believable for polynomials, at least. If I can get this button to, oh, come on. Oh, my pen just ran out of battery again. That's no good. Sorry. Let me charge this thing up. When you're dealing with polynomials, it's pretty believable that something like this sort of ought to be true. Right, does that seem reasonable to everybody? Oh, yes, I would like to borrow your pen, and I'm going to simultaneously charge. Yeah. Thank you. You can just set it right there. I hope it works. If I can get this thing. All right, I got it. Okay. All right, let me just pop this in, and hopefully in a few minutes, that'll be charged back up. Yeah, I pulled a muscle in my shoulder at the gym yesterday. It's just a weird, I don't know. I've got a doctor's appointment. We'll find out what happened, but it's just, I think it'll be okay in a week or two. Yeah. Thank you. Appreciate it. Okay, let's see. Does it work? Yes, it does. Okay. And does it have eraser buttons? Yes. Okay, awesome. Okay, we're in business. Okay, so for polynomials, it's kind of believable. Now, what about, though, for other functions that aren't polynomials, like exponentials and logs? And if you try to take a sort of a symbolic, approach to, how would I persuade myself that this actually works? It's not immediately clear how you would do that, and it's pretty non-obvious. But it does turn out that it's usually true for most non-polynomials. So, for example, what I have here is kind of bulky notation. But basically what this is saying is that once certain conditions are satisfied, if you just rearrange the order that you write down the partials, rearrange them in whatever order you like, cool, no problem. It's always going to give you, certain conditions being satisfied. You will get the same thing no matter which order you do the partials. Okay. There is a important catch, though. The important catch is that the function has to have this regularity condition called CK. And CK means that however many partials you're talking about doing, you need for that many of the partials of the original function to be continuous. right? So the C is for continuous, and the K is for how high of an order of the partials all have to be continuous. So what's nice about this is it will answer certain questions for us immediately. Yeah, go ahead. Yeah.
Does it have to exist for all the variables or only the variables?
Yeah, no, for all of them. Yeah, you do have to check all of them, and it's kind of annoying. Yeah, but very often not a problem. As follows: imagine if you're looking at a function that's let's take e to the power of x cubed plus y squared z to the 7th minus x to the 4th, something like that, right? E to the power of a polynomial. Not much trouble to persuade yourself. Every one of the partials will be, polynomials times exponentials to the power of polynomials. There's only so many things that can happen, right? And you're always going to get always clearly continuous functions, right? And so in some cases, it's pretty easy to persuade yourself that those partials exist or in continuous, even if you haven't even computed them yet, just from sort of form, sort of structure reasons. Does that make sense to everybody? All right. So, nice fact. Let's talk about what they look like. What does a second partial look like? So this is another question of calculus of what kind of a picture. We're going to talk about this on graphs. So this is going to be part of our calculus of graphs. So keep in mind, what we're about to discuss here only applies to graphs. It doesn't make you can't make any such interpretations about level sets. Okay, so let's talk about what we call unmixed second partials, fxx. How would I interpret fxx? This is an easy one, as it turns out, because taking the x partial of the x partial really is just a matter of treating y as a constant and then literally taking a second derivative, a single variable calculus second derivative with respect to x. And we already have a geometric interpretation of second derivatives. So with y being a constant, and I'll see if I can do this with my left hand, y being a constant, that's pretty good. That cross section is going to be some curve like that. That is clearly concave down, right? Concave down, when you take the second derivative, gives you a negative value, and that means that the x second partial is going to be negative. Everybody happy with that? Okay, likewise, let's see here. Let me erase that. Likewise, if you were to look at the y second partial, you'd be looking at that curve. The y second partial, at least as drawn in this picture, would be positive because it's concave up in the y direction. One thing that's kind of interesting about this is you'll notice there is no single variable version of this, right? Second partials, it's single variable, concavity. End of story. There's only one direction in which to talk about concavity, because there's only one direction, right? Here, because there's two directions in the domain, we can talk about the concavity one way or the other way, and they don't have to agree, right? So multivariable calculus brings up there's more room for things to get weird, and little oddities like this that don't exist in single variable can exist in multivariable. And by the way, this is far from the worst of it. There's some really interesting sort of what you might loosely call counterexamples of weird stuff that doesn't happen in single variable that can happen in multivariable because, again, there's more room to move. All right. Now here's the tricky one. What if we want to talk about a mixed second partial? Right? So we're going to talk about the y partial, but I want to know what does it look like if I take the x partial of the y partial. Right? Is this concavity or something, or what's the deal here? How do I make sense out of this? okay, there is no single variable version of this. I can't say, I'll just, one of the variables is constant and just, and then single variable calculus ensues. Because keep in mind, for this first partial derivative, when we're doing the y partial, x is constant. But for the second partial derivative, x is no longer constant. Now x is a variable. Now y is constant, which had been the variable previously, right? So you can't turn this into a single variable calculus problem. So we're just going to have to kind of brute force an answer to this question. And here we go. I'm going to start by first trying to make sense of the y partials. Y partials, of course, say you're going in the y direction. I'm going to interpret these as slopes of tangent lines. And now, apologize for the picture here. Editorial decision as I was drawing this picture. It actually makes the picture more confusing if I try to draw the surface, right? So use your imagination. Pretend that there is a surface here that is the graph. But whatever that surface is, I'm going to be, as I am going in the y direction, I'll be looking at a tangent line to the surface that's kind of tangent as I go in that y direction. And for example, it might look something like that, let's say. Likewise, at other points, like here, I can talk about what it looks like to go in the y direction and what that tangent line in that direction might look like. And likewise here, tangent line might be that, and here, tangent line might be something like that, and here, tangent line might be something like that. Okay, now, fine. This is a bunch of geometric representations of y partials because those y partials are slopes of tangent lines as I'm moving in the y direction. Is that cool? Okay, that's not what we wanted to understand. What we want to understand is what does the x partial of the y, what does the x partial of the y partial look like? Get off of there we go, okay. X partial of the y partial. Tempting to say, okay, well, let's understand the x partials as being slopes in the x direction, but I can't. Sticky, critical point though. When you're talking about interpreting a partial derivative as a slope, you have to be looking at the graph. Here, I'm taking the x partial of the y partial of f. This is not a graph of the y partial of f. This picture on which we're doing our work here is the graph of f. I do not have a graph of the y partial of f. So I can't interpret the x partial that I'm taking in a sloped context because I don't have a graph to work on. Does that make sense to everybody? So I've got to take a different point of view here, and thankfully we have a different point of view. You may recall this different point of view is to say, look, x partial means as you're moving in the x direction, right? As you're doing that, here's me moving in the x direction, right? As I'm taking the x partial. The x partial says, as I go that way, how do these things change? How do the y partial, how do these slopes change as I move in the x direction? And now let's just look at the numbers here. Back here, this slope appears to be, I'm going to say -2-ish, right? And now, as I move forward, as I move in the x direction, my slopes go from like -2 to like -1 to like -0.5 to about 0, and then up to about +0.5. In particular, as I go in the x direction, I'm going to try to do this now in imagine the 3 space here. As I go in the x direction, the y partials are increasing. Everybody see what I'm talking about there? Okay, so they were steep negative, and then they increase to become more sort of positive. Now, what does that look like? Is this a picture of concavity? No. This is geometrically, this is not. But now imagine, again, watch my hand here, and as I do something kind of like this, and I tried to draw it in the picture here, but again, it's hard, right? But as I do this, it's, I think, a reasonable interpretation. This is a twisting of the surface, right? Can everybody see kind of there's sort of a twisting happening there. Does that make sense? So this is an interpretation. The y partial of the x partial. Let's see. I will do like this. The y partial of the x. The x partial of the y partial represents that twisting of the graph of f. There is no single variable version of this. So brand new concept. Is everybody cool? All right. Okay, moving along. I'm going to jump up into Chapter 3 real quick. The purpose of this is to allow me a certain point of view in Section 2.5 that we're going to get to in a couple of minutes. There's a really nice point of view that I think is valuable that I just really want to be able to use. So, quick jump up into Chapter 3. This is really no big deal. Y'all remember parametric curves. Remember the idea of a parametric curve? We have position as a function of a parameter, which in practice most of the time we think of as time. So position as a function of time. All right, well, let's take a derivative matrix here. Here's the derivative matrix. Keep in mind there's only one input variable, and that's why there's only one column here. All right, remember, columns correspond to input variables. You only have one input variable, you only get one column. Okay, now, here's a different point of view. Let's just look at the regular old, like naively just the derivative. Calc 1, just, limit of blah, blah, blah. The usual formula for derivatives. We can write that down for a parametric curve. It actually makes sense. There's kind of nothing wrong with this. In the numerator here, we have a difference of two vectors. No problem. We can subtract vectors. We're going to need to take that and divide it by a scalar, h. Cool. Vector divided by scalar, not a problem, right? Everything makes sense. We can totally work it out. So that's kind of a nice observation to make then, is that the derivative matrix can be thought of as just a regular old single variable derivative of this parametric curve. Now, what does this look like physically? I observe that the numerator here is a displacement. About like that. At time t, I was here. At time t plus h, I'm there. Right? So if you were here and then you go to there, the difference is called the displacement vector. Okay, so now what is the denominator down here? The denominator says how much time elapsed between t and t plus h. So it's a pretty immediate result then. This expression is literally talking about displacement per unit time. And that's an existing physics concept called velocity. That makes sense to everybody? And then you can also furthermore kind of look at what happens in the limit as h approaches 0, and think about what happens as this point kind of comes closer and closer back down to this point, and these vectors become closer and closer to being what the limit is, which is tangent. Well, if I could draw tangent. There we go. Tangent to the curve. Right, so altogether, the velocity vector is pointing tangent to the curve, and the magnitude is equal to the speed. And again, there's an existing old physics concept. Okay, and then likewise, by the way, the derivative of the velocity is acceleration. Everybody good? Okay. Let's do an example. Y'all have probably done examples kind of like this, sort of single variable versions of these examples involving position and acceleration and velocity, and which one is the derivative of the other, and such is the antiderivative of whatever. And so this is going to be very, very similar to what you saw in those single variable versions. We're given, in this case, a velocity and an initial location. And from that, we want to find the acceleration and the position. Okay, the first part is easy. Acceleration is the derivative of velocity. So, quick little derivative, one component at a time. Boom, there's your answer. That's the acceleration. Everybody happy with that? All right. Okay, now here's where it gets a little tricky. What is position? I'm given the velocity. I want to find the position. Wait, I know that velocity is the derivative of position. So think about that grammatically. If velocity is the derivative of position, then position is the antiderivative of velocity. And that's what I've got written down right here. Position is the antiderivative of velocity. And then it's just a matter of doing it. You take antiderivatives one coordinate at a time, just like you take derivatives one coordinate at a time. And don't forget, when you do anti-differentiation, you always get in each one of these coordinates here, there's a plus c, and therefore between the two of them, you have a plus c vector that results. So don't forget about that plus c vector. Everybody good so far? All right. Now we evaluate that constant by plugging in. Here we go. Let's see here. I'm going to look at this. I'm going to look at this equation. I'm going to choose to plug in t equals 0. And the reason I'm going to plug in t equals 0 is because I know what happens when t equals 0, right? So that's how you make the choice. You decide what value of t to plug in based on, well, what value of t do you know something, right? I happen to know something here for t equals 0. So fine, we'll plug in t equals 0. I've also got to plug in t equals 0 into here, of course. And doing the arithmetic, what comes out is that green equation turns into this green equation. Everybody okay? Right, and then of course it's easy to solve for c. Okay, and then we're done. Everybody's happy? Here's the thing to be careful about. A lot of students get this wrong. There is a mythology out there. I'm going to do this in red to emphasize that this is not true. A lot of students got out of their high school calculus classes thinking that the integration constant must always equal to the initial value, and that's just wrong. It's kind of clearly wrong. Certainly in this example, perfectly obvious. Here's what c is. C is clearly 2, 5. That's not at all the same as that, right? So it's a weird thing to me that this mythology persists. I think it's because high school teachers in a lot of cases are just a little bit lazy in their examples. And let's trace through real quick and see how this would play out. What would happen if the given velocity was all polynomials? Then these would be polynomials. These right here, I'd be taking antiderivatives of polynomials, which if you think about it, antiderivatives of polynomials are other polynomials which always have a factor of t. And what happens when you plug in t equals 0 into a bunch of polynomials that all terms have a factor of t? Well, all terms have a factor of t. Everything's going to get multiplied by 0. That will become 0. That'll make this a 0. And that'll make, as it would turn out in such a case, your integration constant, seemingly coincidentally, would be equal to your initial value. So it's an illusion. It's a kind of a relic of an unnatural choice to always use polynomials and things, right? And it just doesn't make any sense in the real world. So anyway, make sure that you're clear on this. You cannot just assume that your integration constant is going to be your initial value. Absolutely does not work. And I want to say another quick thing about this. There's really two problems with it. For one thing, you'll get a wrong answer, very possibly, right? But keep in mind, this course isn't about answers, right? So very important. It's a philosophical point about the course itself. This course is about ideas and reasoning. So the fact that you would get a wrong answer, probably, not the point. The point is that any sort of claim that integration constants must be initial values is just invalid reasoning. It's a total non sequitur. That's the problem, right? So in particular, you might actually get lucky. I might someday actually make a question where it's, yeah, in fact, the velocity is all polynomials. If I do that, then this invalid reasoning would actually get you the right answer. And it's still invalid reasoning, and that's still the point. I hope that makes sense to everybody, right? So don't hope to get lucky. Invalid reasoning is still invalid reasoning, no matter how lucky you might happen to get with the conclusion. Okay. All right, enough of that. Okay. Real quick, there is some stuff about Kepler's work about planetary motion and stuff like that. Later in this section, you'll notice on the content syllabus that's excluded from the course. Right? You are not responsible for the Kepler stuff. That said, I am going to recover these two formulas here. These are very handy here and there, and they are very general, and I think this is appropriate to know. So this is officially part of the course. Do make sure that you know these. Notice they're just kind of product rules, right? They're kind of exactly what you would expect. In fact, if you didn't know anything about any of this stuff, and somebody asked you, what do you think this ought to be? What do you think these ought to be? I'll bet you this would have been your first guess. Right? So they're really easy to remember because they just look exactly like you feel like they ought to look. And so that makes them easy to remember. Anyway. Okay, let's see. I hope my pen let me see if my pen is working again. Fingers crossed. Okay, it is. Do you need your pen back?
That's okay.
Okay. All right. Well, maybe I'll keep it as a backup just in case here. If I can get that thing off. There we go. Okay. All righty. Okay, moving along. Into section 2.5 now. So, a lot of stuff to say about the chain rule. One of the things that you're going to notice about the way I like to approach multi is to find a point of view on single variable calculus that extends very naturally to multi, right? I'm a big believer. I think this is really useful in a lot of cases. This is going to be one of them. So I'm going to give you a point of view here on what a derivative is, and I'm going to give you a point of view on how to sort of take that perspective and make sense out of the chain rule. I know you know all this stuff, right? The purpose of this page is not to teach you stuff you don't know. The purpose of this page is to set up a pattern that we're going to extend on the next page. So the pattern that we're going to use here, we're going to start by thinking about derivatives. So what is a derivative? And a derivative, as I've got it set up here, is something that you multiply by input velocity to get output velocity. And I know that there's a million different points of view on how to think about a single variable derivative. This is the one that's going to make life good for what we're doing here. So hopefully this rings bells. Let me point out, if maybe you're uncomfortable with this, if you rewrite x prime as dx dt, And if you rewrite y prime as dy dt, really this is just a statement of the single variable chain rule that, again, I know y'all know, right? So anyway, that's one way to think about this, but again, I don't want to think about it that way. I want to think about it as this is an interpretation of what derivatives do. Derivatives are factors. They're factors that turn input velocities into output velocities. Is that cool? All right. Now, with that point of view in mind, let's compose some functions. Here's a function. This is all single variable. Y is a function of x. Here's another function. Z is a function of y. Now I can compose those. I can take the output from f, make that the input to g, and all together my original input x gets turned into my eventual output z. So the composition makes z a function of x. Right? Familiar? Okay. All right. So, let's see here. Different way you can think about the derivatives. Notice there's three functions on the screen here. Each of those three functions, I can talk about the derivative. Each of those three functions, I can interpret the derivative as a statement about what you multiply by input velocities to get output velocities. So these three equations here are really just all, this above interpretation of derivatives as applied to these three different functions. The first one, the second one, and the composition. Now, one thing you could do here, and I've written out the algebra, and you can look at this if you like. I better zoom out so we can fit this all on. Whoa, too much. There we go. You could, as I've written here, plug in the first equation into the second equation, compare with the third equation, and you can get lost in the algebra. Not that bad, but you can take an algebraic point of view on this, and that's fine. But I prefer to take the following hand-wavy, intuitive approach. When you do what f does, the derivative of f is a multiplicative factor. That's how fast that's how much you're multiplying by the input velocity to get the output velocity. And then when you then take that output velocity and look and see, well, what about its output? Well, now you're multiplying by another factor. And altogether, what have you really done then in the combination of those two steps? What you've really done is, well, let's see, I multiplied by this, and then I multiplied by that. Altogether, I've multiplied by the product of this and that. Right? It's not a particularly deep observation. If I multiply something by 3 and then I multiply the result by 4, altogether I've multiplied by 12. Right? That's all that's going on here. And so that's really all the chain rule says, is that when you have a sequence of factors, you really have a product of factors. Is that cool? Does everybody kind of see that happening here? All right, and a different point of view you can take is that I really like how this rolls off the tongue. Differentiation turns a composition into a product. We were composing functions. We were looking at the composition of f and g, and taking the derivatives gives me the product of the derivatives of f and g. So what had been a composition turns into a product. All right? Okay. Quick summary. We have a specific point of view on derivatives. We apply to the composition here to each of the three functions in a composition, and then just observe that, multiplying by one thing and multiplying by another thing, altogether you multiply by the product. Okay, now all that in mind, let's do the same thing in a multivariable context. We'll start off with how to view a derivative. A derivative, we've already established, you can think of as being something that you multiply by an input velocity to get an output velocity. Right? It's a factor. Just like in single variable calculus, it's a factor. Now, in this case, it's a matrix factor, right? It's something that you're multiplying by a vector to get another vector. So sure, this is different. In single variable, it was a scalar multiplying by a scalar to give you another scalar, but whatever. It's a multiplicative factor, just like it was in single variable calculus. Okay. Again, we can take a composition. Right? So here's a multivariable function. Here's another multivariable function. I can look at the composition. The composition is, the original input leading to the eventual output. And each of these three functions, I can write down the above interpretation of their derivatives. Right? So the derivative of f is the thing you multiply by x prime to get y prime. The derivative of g is the thing you multiply by y prime to get z prime. And the derivative of the composition is altogether the thing you multiply by x prime to get a z prime. Okay. And again, now you can take a sort of a algebraic approach to trying to bring all this together, but again, I think it's easier just to sort of think intuitively. What do I do when I'm applying the derivative there? I'm just multiplying by the factor. That's what derivatives are. They're just factors. And then what am I doing when I apply the derivative there? Well, I'm multiplying by that factor. And altogether then, the derivative of the composition is the kind of the combination of what you get when you do first the green and then the blue. In other words, altogether we're multiplying in the composition. We're multiplying by this product of factors. And that gives us our multivariable chain rule. And it's a statement, as you see here, it's a statement about derivative matrices. And the derivative matrix of a composition is the product of the derivative matrices of the individual functions. Does it kind of seem reasonable? Notice the analogy between the argument and the result here versus the argument and the result here. Same ideas. Factors times factors give you factors. It's just that now they're matrices. Okay. All right, let's see here. Real quick final observation, and then we'll call it a day. Notice that in the picture here that I've drawn, it was a two-dimensional sort of x space, and then a two-dimensional y space, and then a two-dimensional z space. Notice also that didn't play into my argument at all, right? All I did in my argument is talk about how, well, the matrix is the thing that you multiply by this to get that. The fact that this is a two-dimensional world and that that's a two-dimensional world, this business about multiplicative factors works no matter what those dimensions are, right? So this result here is not specific to two dimensions. This works in any combination of dimensions. You could have a 7-dimensional domain going to a 12-dimensional, whatever this is, going to a 14-dimensional eventual target. And sure, these matrices will be bigger matrices, but it remains that the derivative of the composition is the product of the individual derivatives. Okay, and now that makes for a pretty good stopping point, so why don't we draw the line right here. And y'all have a good weekend. I'll see you on Monday. And if you came in